Good evening, students. This is Econ 215, Chapter 2 lecture video. And this chapter is on the multivariate, or I should say linear equations with two variables. It is not, I guess, should not be very difficult because this is still a review material for you. But of course, I hope you are studying and reviewing in preparation for our class and for future chapters of new content. Okay, so now this particular chapter is important because this is what we can start to relate to economics a little bit, right? So we'll start with the very basic of equations with two variables, and like you have hopefully studied, when you have two variables, then you are looking at graphically, you're looking at two axes, and you can create a graph that's called a Cartesian coordinate system or Cartesian plane. Okay, so you'll have a vertical axis, okay, and a, oops, hold on, horizontal axis, okay. And usually we mark the horizontal axis as x, the vertical axis is y, okay. And now in this Cartesian coordinate system, every point gives you two pieces of information, right? So we call where they cross each other the origin, these two axes, okay? And, you know, if we have a point right here, this point tells you two pieces of information. First of all, it tells you that the value on the horizontal axis is 3, for example, and the value on the vertical axis is 2. Okay, the way we represent this is saying this point, call it point A. Okay, point A is recorded as parentheses 3, 2. Okay, now this way of presenting information is designed for this two variable world. However, I realized that just last chapter we were talking about sets and etc. And then this looks just like a set, saying if there was a set from going from 3 to 2, right? So it is confusing, but that's why the understanding the context is very important, right? If you are saying that you're solving for an equation with two variables, then clearly this is a point in your two variable mathematics world. But if you're talking about sets and solving for, you know, or representing a group of numbers, then this would be a set not including the endpoints in the set. Now, of course, there's no set going from 3 to 2 normally, but so that can be another clue of what this can be representing. Now, another thing is with this point A, okay, we always represent the horizontal number first. So 3 or whatever the first number is in your parentheses is always the value on the y, not on the x axis, the horizontal axis. And then the second number is your value on your vertical or y axis, okay? All right. Okay, now also just a quick reminder in this context, okay, the distance between 2 points, okay, of x1, y1 and x2, y2, okay, the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, and so for example, if you try to find the distance between point A and the origin, when you take this formula, what you're calculating, okay, is this distance right there. So that would be the little d, okay? If we were to say, okay, this is point A, which is, okay, so if we're calculating 3 and 2 and 0 and 0, okay, so the distance in that case would be the square root of 3 squared plus 2 squared, which is, okay, the square root of 13, okay? So that would be that little distance right there, okay? All right, okay, I hope that makes sense. And now I mentioned that this kind of a system is relevant for us because in economics, you know, for example, many things you deal with, or you have dealt with so far, have two variables, right? So your demand function usually is quantity equals, okay, negative some kind of constant, call it a little a, times p plus some other constant b. So where a and b are constants, okay, and also positive, right? So because there's a negative sign. So this tells you you have two variables, q, quantity, and p. And the relationship between these two represent this equation with two variables. And that's why when we draw a graph in economics, okay, we don't usually do past the origin, but okay, we do have quantity down here, price down up there, and a zero. Then you have some kind of a equation, okay? So some kind of graph, right? So this is your demand curve, which is represented by your demand function, and then you would have a supply curve represented by the supply function, okay? And then any point in this graph will give you two pieces of information, right? For example, a point right here tells you at this particular price, call this P1, okay? And this is the quantity demanded of the market. People will buy Q1 of it, okay? Similarly, at this point, that means that the price of P1, okay, I should say this is Q, let's call this Q1S, and this is Q1D, so you know one is quantity demanded, one is quantity supplied. But that's kind of the world you've been living in with two variables on the equation and this coordinate system we draw on a graph, okay? So that's why this chapter is relevant, okay? Now, another thing that we use a lot, and you're hopefully when you were doing the learn portion of this chapter, you reviewed, is the midpoint method, okay? The midpoint between 2 points on your Cartesian plane has the following coordinates, right? So we say between, so midpoint between, okay, x1, y1, and x2, y2, okay, is x1 plus x2 divided by 2, then y1 plus y2 divided by 2. Now, you might say, okay, well, that looks vaguely familiar, but what's the whole point? Well, the midpoint method is used very widely in calculating elasticities, right? If you recall, we said the elasticity, the price elasticity of demand, okay, is the percentage change in quantity demanded divided by the percentage change in price. Again, the same two variables that you've been working with. But we said percentage changes are calculated based on comparing to midpoints. What I'm talking about is, you know, let's say your quantity, original quantity is 100, okay? Then your new quantity is 200. Now, if you look at the percentage change, traditionally, if you compare it to quantity 1, you say, wow, my new quantity is twice as much as quantity 1. So that means I have 100% increase, which is not wrong. However, you can also look at that and say, wow, my old quantity is only half of my new quantity. So that is a 50% increase. And that is also a correct perspective to look at it. So to avoid the confusion of how to find the right percentage change, depending on which point is your reference point, in economics, we use the midpoint method, where we compare the percentage change to the midpoint. And thus, okay, the formula for your elasticity has always been, okay, the midpoint method tells you it's the change in quantity, which is Q2 minus Q1, the new quantity minus the old quantity, divided by the midpoint of your quantity. So Q1 plus Q2 divided by 2 times 100. Similarly, okay, for prices, you do P2 minus P1 divided by the midpoint of your price, which is P1 plus P2 divided by 2, then times 100. That is how we calculate your elasticity of demand, and which gives you then how sensitive your quantity demanded is to price changes, right? So for example, if you do all this calculation, you get that your quantity demanded is -3, okay? Now this is the part that a lot of students struggle with, because they say, okay, I got this number, went through this tedious calculation, what the heck is -3? Okay, first of all, because of the law of demand, this price elasticity of demand, how quantity demanded and price work with each other, is always negative, right? Because when price increases, quantity demanded will always be negative. Will always decreases. And when price decreases, quantity demanded will always increase. So the change in these two will always be in opposite directions. So your elasticity is always negative. That's what that first piece means. And then that 3 simply tells you the percentage change in quantity demanded is 3 times of your percentage change in price, right? Because after all, your elasticity is the quantity change divided by the price change. If that number equals 3, that means your quantity change in your numerator is 3 times the size of your denominator change of price. So that means then whenever, in this particular example, right, that means if your price increases by 10%, you're going to lose 30% in sales, okay? And on the contrary, if you drop price by like 10%, you're going to have a 30% increase in sales. So this is actually very crucial information for companies to gather, right? We have had several alumni that have moved on to work for big corporations such as Walmart. And we have had some of them come back and talk to students. And one of our very successful alumni said, you know, when I took Econ 150, I learned about elasticity, totally didn't pay attention, and forgot all about it until I went to work for Walmart. And that's when I realized this is all I do day in, day out. And you know, he was able to make big decisions on millions of dollars of purchases just based on a simple calculation of their elasticity, right? Whether it's worth to purchase something, and if they want to move certain products, do they want to decrease price or not? If so, by how much, right? These are like, again, seemingly unimportant and boring concepts to you maybe, but in the real business world, this is crucial information, right? We have another alum that works for Frontier Airlines, and he said the same thing. This is all he does, right? Because his job is to analyze whether it is worth it for Frontier Airlines to get into a market, and if so, how should they price their tickets, right? Should they charge an arm and leg, or should they be very competitive and offer low fares? And that all depends on the elasticity of demand of that market, right? So anyway, that comes from the midpoint method, which is again reviewed in this chapter. Okay, all right. So now let's look at some specific examples and or just little equations I want you to practice. There's a lot of equations in the book, or on your website, I should say, where you can write them into different forms and then calculate the results, given x equals 1, then what is the value of y? I don't think there's much value for me to do that here, because that's just simple algorithm once you can plug numbers in, okay? But I do want to talk about the equation in different forms in the general terms and then give you some examples, okay? So first of all, when you have a linear equation in two variables, okay, the very general form is ax plus by, okay, equals c, where a, b, and c, okay, are constants, okay, and a and b are not both 0, right? Because otherwise you don't really have an equation, you just have a constant, okay, which is c equals 0, okay? So this is called the standard form of an equation in two variables, okay? Now, with this standard form, okay, when you have just x to the first power and y to the first power and put it into one equation, what you're forming in the Cartesian plane is a single line, okay? So then if you draw a line, right, if you start with your axes here, okay, and this is x, this is y, okay? If you draw a line here, you'll see that these lines are likely going to cross these axes, right? So let's say we have a line looking something like this, okay, like that. And this is your ax plus by equals c. And you can see it crosses your horizontal axis right here, your vertical axis right there, okay? So this point is called your x-intercept. Okay, and this point is your y-intercept. Okay, it just tells you where a certain function crosses at your axes. And you can see when it crosses here, okay, for example, at the x-intercept, what is the value of y? Well, the value of y is 0, right? So to find this x-intercept, you just need to plug y equals 0 into your equation, then solve for x. Then whatever that is, in fact, if you do that, you can see if you plug y equals 0 into this equation for your x-intercept, this becomes ax plus 0 equals c, right? Because y is 0, b times y is then 0. So that gives you x equals c divided by a. Okay, so your x-intercept is always going to be c over a, then 0, because the value of y is always 0, the value of x is always c divided by a. Similarly, for your y-intercept, that is when the value of x is 0, right? So if you plug x equals 0 in, you get by equals c. So that tells you y equals always c divided by b. So that means your y-axis intercept is always 0. That's the value of x plus, not plus, sorry, 0, and then c over b. Okay, that is always the value of your y intercept. Okay. All right. So again, I hope this is not really too complicated. This standard form only works for the first power of variables, right? So you have just x and y, no x squared, no y squared, no x times y, no any of those different other type of powers of variation you can, powers of variables you can have, because once you have those, you no longer have a straight line. That's when you have curves and other shapes, which we'll talk about in chapter 3. Okay, so let's look at a couple of exercises really quick. I'm not gonna draw a whole lot of graphs right here, so let me change this to a white paper so you can see more easily. Okay, so I want you to determine, the following function to see if it is linear, okay? And if it is linear, convert it into the standard form. So this is an example from the book that I have. So it's 7 plus y squared minus y squared equals 9x plus 12, right? So this one has y squared, so it looks like it's not a linear function, but is it? Let's look at it and determine, right? So if we, if you remember last time following the FOIL rule to expand your square terms, okay? So this equals 49 plus 7y plus, okay, 7y plus y squared, right? That's what the first term 7 plus y squared expanded, okay? Minus y squared equals 9x plus 12, and plus squared, minus squared cancel each other. Then 7y plus 7y is 14y, so you get 49 plus 14y equals 9x plus 12. So clearly x and y are both in their first power, so this is a linear function. It's a straight line, okay? Now to convert it into the standard form, you just need to move x and y on one side and then the numbers on to the other. So you have 9x minus 14y equals, okay, 49 minus 12 is 37. Okay, so this is your standard form of this linear function. Okay, now let's look at another example, right? So doing the same thing. Let's say we have a equation where it says 5x squared minus x minus 2 squared equals y plus 9. Is this a linear equation? Well, let's look at it, right? So you have 5x squared minus, okay, then x minus 2 squared is x squared, okay, minus 4x plus 4, okay, equals y plus 9. And if you do that, you can see 5x squared minus x squared only gives you 4x squared. Then minus and minus becomes plus 4x. Then minus and plus becomes minus 4 equals y plus 9. Clearly, you have this term of x squared here, so this is not a linear function. Okay, I hope this makes sense. And similarly, you can, instead of just x having a higher power than 1, you can also have x with a lower power than 1, right? So, for example, you can have 6x plus 7y equals, let's say, 11. This is also not a linear function because if you remember, okay, 1 over x is x to the minus 1th power, right? Minus first power, negative 1 power, and 1 over y is y raised to the negative 1 power. So this really is 6 times x minus 1 first power plus 7 times y to the negative first power, and this equals 11. So clearly you don't have x and y at its first power, so this is also not a linear function. Okay, all right, okay, now okay, so let's look at another quick example, right? If I have 3y plus 4x equals 3y minus 8, okay? And I want you to find the x and y intercepts, what would you do? Well, first of all, you have 3y on both sides. So if you subtract 3y on both sides, then they disappear, right? Because if you have the same term on both sides of the equation, they can cancel each other. The way to do that is, 3y plus 4x minus 3y equals 3y minus 8 minus 3y. Since you're subtracting the same term on both sides of the equation stands, and 3y and 3y cancel here, 3y and 3y cancel here. So all you get is 4x equals negative 8. Or another way to look at it is x equals -2, right? So I should say this, okay? So clearly, okay, with x equals -2, what does that look like? Well, okay, I'm not going to change it back to the engineering paper. I'm just going to draw it like that, okay? So if this is x, this is y, and this is -2 on your x-axis, then x equals -2 is going to be a vertical line that is parallel to your y-axis. That is the function of x equals -2, right? So y can be anywhere for whatever value that it wants to take on, but x always equals -2. So you can see clearly you do have a x-axis where when y equals 0, okay, x equals -2. So you do have an x-intercept. That is -2, 0, okay, when y equals 0. But do you have a y-intercept with this particular function? No, you don't, right? So the y-intercept, I'll just do inner, okay, is non-existent, okay, or you can say absent if you want, okay, because this function particularly does not ever intersect with the y-axis, okay? All right. Okay, so now let's look at other forms of linear equations, right? Because we have talked about the standard form, but another form is to do what's called the slope-intersect form of a line, okay? So slope-intercept, okay, form. And that's when you have y equals m times x plus b, okay, where m is slope of your line, okay, and b is just a constant, okay. And you can see here it's called the slope-intersect form because first of all you do have slope, and then the intersect is referring to the y-intersect, because if x is 0, okay, then y equals b, right? So your y-intercept in this case is going to be 0 for x and then b for y always. So this is useful because if you know a certain line, straight line goes through a point and you know the slope of it, then you can determine, okay, what the function is that forms that line. Okay, and this is the kind of form that your demand curves and supply curves take on, right? So where it says Q equals, let's say, -2 times P plus 23, okay? And if this is your demand curve, okay, you can see that here it is exactly this form, right? Where quantity is dependent on price, and they have a negative relationship, so it's a negatively sloped line, and hopefully that confirms with you that this is your negatively sloped demand curve, or actually better yet, I'll just draw it, right? So price, quantity is negatively sloped, right? Okay, now you might notice that the slope-intersect form normally has the vertical axis and that equals something about horizontal plus a constant. But in this particular case, your demand and supply curves are quantity equals something about price plus some kind of number, okay? And economists know that this is not the traditional slope-intersect form, but this is tradition in economics. Whoever started this did this the wrong way, if you will, and it's stuck. So now you can have what's called the inverse demand function, where you, in this case, you can see P can equal -1/2 of Q minus 23 divided by 2 is 11.5, right? So this is the same function for this particular line, this demand curve. But this just for economists just looks weird because we haven't been writing it in this way forever. And even though this is the more correct slope-intersect form, we use this form, even though we know it's not traditional. Okay. Now, either way, you can solve it, no problem. I just wanted to point that out in case you're wondering why our dependent variable q lies on the horizontal axis while the normal slope interact force form has the vertical axis variable as the dependent variable. Just tradition, okay? Whoever started this, I don't know, but you know, if you ever meet that person in heaven, if that first economist figured this out, made it to heaven, you can ask them, what the heck were you thinking, right? So anyway, all right. Now, I guess just to make sure, I can assume that you know how to calculate your slope, right? So m is calculated by rise over run. Rise really is just this term we use to describe vertical change. And vertical change is always y2 minus y1, right? y2 is the new value for y, and y1 is the old value, divided by x2 minus x1. Now, this is how you calculate your slope. And of course, later as we talk about calculus, which will make all these things a whole lot easier by taking a derivative. But for now, you're stuck in algebra, so this is how you do it. Now, when you have 2 points, if I tell you that, you know, there are 2 points on your demand curve. One is, you know, when the price is 23, quantity, let's say, is 50, right? So something like that. And then the other one is when the price is 46 and quantity is 20, right? So, okay. If you have these 2 points and I ask you to find your demand curve and figure out what the slope is, you might say, well, which point is the first point? Which one is the second point? Turns out it doesn't matter as long as you keep the order consistent between y and x. What I mean by that is if you decide that 23 is your old value and 46 is your new value for price, okay, then you better treat 50 as the new value and 20 as the old value for quantity. Okay, so if what I'm saying is if this is y2 and this is y1, then this better be x2 and this better be x1. Okay, and now if you want to treat you know, this one as x1 and y1 and this one is x2 and y2, you can do it and the result is exactly the same. You're going to get the same slope, but the key is you cannot take 1 point and say in the y value this is the new value, but in the x this is old value, and switch it. Okay, so always keep consistent with what is new and what is old. Okay, all right. Okay, now so let's just do a quick exercise, right? So if you have 4x minus 3y equals 6, okay, how do you change it into the slope-intercept form? Well, hopefully, when we do examples, you've been pausing and then working on this on your own and then coming back to see the solution, right? So to do this, you know, you can say, okay, this is, first of all, I want to change it to 3y equals 4x minus 6, right? Then I divide everything by 3, you get y equals 4/3 of x minus 2. Okay, so this is your slope-intersect form where we say, okay, the slope is 4/3 and the intercept for y is 0 and -2. Okay. All right. Okay. Now the last form that a linear function can take on is called the point slope form of a line. Okay, so point slope form. Okay, that is when you have an equation for the line passing through a specific point and you know the slope like we talked about. Okay, so the point is not just your y-intercept, but some other point with x1 and y1. So if, let's say, you know, okay, the point, this line passes through x1 and y1. Okay, here x1 and y1 are values, not variables. Okay, so, and the slope, okay, and slope is m. Then the general form, I'm doing this in all letters because I want to give you the general form. The general form is y, the variable, minus y1, the value, equals m times x, the variable, minus x1, the value. Now let's do an example with numbers. Let's say that you know a certain line passes through 5 and 16, and the slope is 2. So the function for that line that passes through 5 to 16 at the slope of 2 then is y minus 16 equals 2 times x minus 5. Okay, and then you can then, if you want to change it to other types of forms, then you can start working there to change it into the standard form or the slope-intercept form. Okay. Now remember that vertical lines cannot be described in this form because vertical lines, what happens to their slope is undefined, right? Because horizontal line slope is 0, but vertical lines, there's no defined slope. So this form does not fit every type of line there is, okay? All right, so those are the 3 different forms of a linear function. I hope you can see they're all just interconnected. There's no big difference except what is convenient for what kind of information you want to extract quickly, okay? So now let's see. I guess we can do some practice, right? So let's say, again, okay, once I give you the question, pause it and then try to solve it before you come back for the solution, right? So let's say we know a line goes through the point of -2 and 11, and it has a slope of -1/3. Then I want you to give me the slope intercept form of this equation, right? So the easiest, since this point is not your y-intercept, so the easiest way is to start with the slope, the point slope form, where you say, okay, well, if this is the case, I know my equation is y minus 11 equals -1/3 times x minus -2, which is plus 2, okay? And then to change it into the slope-intercept form, you need y equals, okay, -1/3 times x, okay, plus, okay, 11 plus, well, actually, no, let's do 11 at the end. So now plus, because it's -1/3 times 2, so it's -2/3, okay, plus 11, because I'm adding 11 to both sides, and the 11 on your left side is canceled out because it's -11 plus 11 on the left-hand side. On the right-hand side, it's just plus 11, okay? Now we just need to combine the -2/3 plus 11, and then that gives you y equals -1/3 of x, okay, minus 20, let's see, am I doing this right? Yeah, so minus 29, no, plus 29, right? Plus 29 divided by 3, right? Okay, so this is the form that we're looking for, where y equals something, the slope times x plus a constant. Okay, all right. So I hope this makes sense, and if not, then definitely go back and review some more and do a lot of practice. Okay, and All right. Okay, and also in your study examples, there should be some story questions. So make sure you work on those, right? Because that's more important than or more relevant to economics than just pure math. Okay. Now, if you have questions, make sure you write those down, and we'll talk about them in class on Thursday. I'll be happy to answer those. Okay. All right. The next thing I want to talk about is parallel and perpendicular lines. Okay. So parallel lines, hopefully you all understand, that means they have exactly the same slope. So they have the same slope, but they go through different points. And if you have two functions that have the same slope, but different constants, then that tells you they're parallel. Okay. Now, perpendicular lines are more interesting, right? So if two lines are perpendicular and none of them is vertical, because, well, once it's vertical, we don't have any defined slope. But if they're perpendicular and not vertical, then M1, the slope of one line, is going to equal 1 over M2, the slope of the other line. So if they're perpendicular, the slope of one is going to be the negative inverse of the other. Okay. So of course, if you do have a vertical line, then the perpendicular is the horizontal line where slope equals 0. But since vertical slopes are not defined, we can't do this in this form. But if you have any other lines that's not vertical, then let's say if you have y equals 3x plus 15, then you have another one that's y equals negative 1/3 x plus 8. These two lines are perpendicular, okay, because the slopes right here, okay, right here and right here, satisfy the rule given right there. Okay. All right. Okay. Let's see. I think you can practice and try to convert different forms of lines to see if they are perpendicular or not, right? And let's do a quick example. Let's say that you have two functions, okay, two lines, or two equations, I should say. Now we haven't gone to the function part yet, okay? So which is negative 4y plus 2x equals 12. And then you have 3x minus 2x plus 1 equals 2y minus 3x, right? The question is, well, okay, are these two lines perpendicular? Okay, so let's figure it out. Okay, to do that, you first want to change the equations into the slope-intercept form. That way you can look at the slope by itself very easily. So the way to do that then is to say, okay, this one, okay, gives me, I move negative 4y to the right side of the equation and 12 to the left side of the equation. So I get positive 4y equals 2x minus 12, okay? And if you don't know how I got here, then you need to go back and review how to move things from one side of the equation to another, because I really expect you to at least know this by now, okay? So then you divide both sides by 4, you get y equals 1/2 of x minus 3, okay? Similarly, on this equation, okay, it's a little bit more complicated. We have 3x minus 2x minus 2 equals 2y minus 3x, okay? So that gives you x minus 2 equals 2y minus 3x. So you want to move the, whoops, that's not what I wanted. Okay, you want to move negative 3x from the right-hand side to the left. So this gives you, okay, 2y equals x minus 2 plus 3x. Okay, I just put the 2y on the left-hand side because that's what eventually we want. This then gives you 2y equals 4x minus 2. And divide both sides by 2, you get 2y equals, y equals 2x minus 1. Okay. Now the question is, are these two equations perpendicular? Well, hopefully you figured out the answer is no, right? Because even though here, this is 2 and this is 1/2 looks similar, but remember the condition is m1 equals negative of 1/m2, right? So we don't have the negative part. So these are two positively sloped lines, and they cannot be perpendicular to each other. If a perpendicular line to a positively sloped line has to be negatively sloped. Okay, so but anyway, so this is kind of what you can look at here. Okay, now the last thing that in this week we jump back a little bit to chapter 7 and talk about inequalities. Okay, and linear inequalities in two variables. The reason for that is because in the last chapter we talked about inequalities with one variable. So now that we have expanded our horizon to two variables, we want to understand how the inequalities are solved in two variables. Okay. Now the way to solve for the purpose of your understanding for this class and future econ classes, the way to solve linear inequalities in two variables, there are 3 steps, right? So so step number 1 is to graph the line that results from this inequality by replacing the inequality symbol with the equal sign. Okay, so 1 is graph the line, okay, from replacing the inequality symbol. Oops, okay, with your equal sign. That way you turn an inequality into an equation so you can actually draw that line. Okay, step 2 is you mark the line solid. So you draw this line, but so you draw the line solid if you had a less than or equal to or greater than or equal to, there's an equal to part to your original inequality, okay? Or if you do dotted line, okay, if you only had less than or greater than, there's no equal to, okay? So if you do dotted line, then that means there was no equal to part of your inequality. And the difference is the solid line is included in the solution for your inequality, and the dotted line is not included. It starts right beyond it, right? So now the step 3, okay, is you determine which of the half planes determined by this boundary line you drew on the coordinate system solves your inequality by finding a test point on one side, finding the value of that test point for x and y, and then plug those values into your inequality and see if the inequality is true or not. Okay, so you determine which half plane is the solution by finding a test point and plugging into the inequality to see if it's true. Okay, so If you find a test point, plug it into the inequality is actually correct, okay? Then you know that that area, that side of that line you drew where the test point came from is your solution. Otherwise, the other side of the plane this line divides is the solution, okay? So let's look at some examples. I know talking about this is kind of hard to imagine, okay? So let's look at an example, okay? So I want you to graph the solution for the following, okay, inequality, right, where you have 2x plus 2y is less than -6, okay? So let's draw this really quick, and okay, so this is x, this is y, this is 0, then we do 1, 2, 3, 4, 5, 6, 7, 8, 9, then I guess x is where 10 is, but this is -1, 2, 3, 4, -5, and then 6, 7, 8, 9, -10 right here. Okay, similarly 1, 2, 3, 4, +5, and -1, 2, 3, 4, -5, right? So it gives you an idea of the scales here. So the first step is to draw the line as the equation of 2x plus 2y equals -6. Okay, that's step number 1. And if you do that, you can see, okay, the easiest way to do this is to find where your intercepts are, your x and y intercepts, right? So when x is 0, you have 2y equals -6, which is y equals -3. So that means when x is 0, okay, y is -3. That's this point right here, okay? That's your y-intercept. And similarly, when y is 0, you plug that in, you have 2x equals -6, so x is -3. So when y is 0, x is -3, so then all of a sudden you have this point. Now, I mean, these 2 points, these are your 2 intercepts. So connecting these 2 and then expanding in a straight line, this is your line for 2x plus 2y equals -6. However, since here in the original inequality, there is no equal to part, right? There's just less than -2. You don't draw a solid line. So you have to connect these 2 with a dotted line, okay, and keep extending it and just make sure it's straight. And this is the line then that divides your plane into 2 parts, right? The second part, okay, well, we already did it, which is to make sure this is the dotted or dashed, whatever you want to call it, okay, dotted line. And the third part is to pick a point and just plug it in to see which side of this line is true, right? So let's say, you know, let me change the color here, okay? So this half is all red, okay? And then this half is all, let's see, what color should we do it? Let's do brown, okay? So one of these halves is going to be the solution to this inequality, because when you have a 2-variable inequality, the solution is going to be an area, okay? So you can see the easiest is to pick the origin, right? If I want to say, okay, let's test by picking the origin, right? So test, okay, with the point 0 and 0 and see if this holds. Okay, clearly it's not the right color. Okay, so if we plug that in, 0 and 0, then you get 0 plus 0 is less than -6. Is that right? Is 0 less than -6? Wrong. So that is not true. So that means this test point, which is from the brown side, is not the solution. Okay, so the red side, anything to the left and lower side of this dotted line marked in red, that then becomes your solution for your inequality. I hope that makes sense. If you want to verify, you can always just pick any point on this side, like right here, and then plug it in, and you'll see that that point does satisfy the inequality. So this is how you solve it. Okay, now this becomes a little bit more interesting when you have a system of inequalities you solve at the same time, right? You say, well, I have 2x plus 2y less than -6, and okay, maybe let's say x is greater than 1, right? So if that's the case, let's say greater than equal to 1. Let me draw a different color, and that function would be a vertical function, right? So okay, so this would be your x equals 1. And then if the inequality is x is greater than or equal to 1, because that makes it a solid line, and that means anything to the right-hand side of this function is going to be the solution, right? Any time x is greater or equal to 1, which is to the right-hand side of this green line. So if these two have to be both satisfied, then all of a sudden your solution to this particular system of inequalities is going to be between these, the dotted line and the solid green line right here, right where I marked as green, okay, so that is your area for your solution. Now, if you have a third condition, if you have and something else, then you could have a third line, which then will define either a triangle or it'd be undefined and it'd be a null set. There's no solution that would fit all three, right? So unless it's a parallel line to one of these two, then it won't be a triangle. But if it's not a parallel line to either one of these two lines we already drew, it would form a triangle, and that would be a particular set of solutions, and any point in that triangle would be satisfy all three inequalities in that case, right? So that's kind of the inequalities and the use of it. Now it might seem vague, and I know it is right now, but as you move on, oftentimes you have a system of equations or inequalities that you need to solve together, right? And so for example, if you have a price floor, then that is really an inequality, right? That means is you're looking at all the possible quantities with, let's say, price equal to or less than or equal to 5, then you would have that inequality system you're trying to solve. And then at the same time, if there's some other conditions in there, if there's also a quota, right, and then say quantity has to be less than 20 million, then all of a sudden you have a you have a horizontal line for the price restriction, which is an inequality. Then you have a vertical line that restricts your quantity. Then together, where the market can exist is defined, right? So that is how we use inequalities and solve for inequalities with two variables. Okay. All right, so that's all the key points I wanted to talk about. Holy cow, it's past midnight. Yeah, I'm a night owl. Plus, this is the only time I had during this whole day. So anyway, I hope this video, you find it a little bit helpful, and please write down your questions and we will talk about them on Thursday. Okay, I will see you guys soon.